Good day, Math 30-1s. Today we continue with our conversation about the first chapter, transformations, and we finished with translations, and today we start talking about reflections. And this is sort of broken up into two parts, reflections and then eventually stretches. So to start our conversation about reflections, we really are considering only flipping graphs. But what's new from this year, from last year to this year, is that not only are we flipping vertically like we did in quadratics, we're also going to be flipping horizontally. Now there are a few prepositions that can also be a little bit misleading or tricky. So there are some words like about, in, or on, and these all refer to the same thing. So what we're going to do in our first investigation is to reflect the graph on the left about the x-axis. Now it does help to clearly identify what is being referred to as our sort of flipping location. And so if we're reflecting about the x-axis, or in the x-axis, or on the x-axis, or sometimes as you're going to see it about the line y equals 0, in the line y equals 0, on the line y equals 0, it's sort of all referring to the same thing. And this is a vertical flip. So what gets to be a little bit tricky is seeing x-axis, but knowing that it's referring to a vertical flip. So the flip is about the x-axis, which is referring to a vertical flip. And those two can be a little bit tricky. If we do a vertical flip, what we're basically talking about is all of these points are flipping from a positive to a negative. And if there were any on the negative, they would flip to the positive. So we could take this point A and flip its y value, which is currently at a 0, and say it's still a 0. The b value is currently at a positive 2, and we could flip it to the bottom and say negative 2. If you wanted to give it a new label like b prime, we could, and just say that the path from A to B should also flip the same. We could do the same thing with C, flips from a positive 2 to a negative 2, noticing that we travel straight down horizontally and arrive at our new y value. D value goes from 3 to negative 3, E from 3 to negative 3, and if we continue the pattern, we see sort of a rocket jump. Now, all of these would be a C prime, D prime, and E prime, new letters for their new location. Now this was a vertical flip. The language for a horizontal flip is going to refer to about the y-axis, in the y-axis, on the y-axis. Or, as we commented on the other side, we might see the phrase reflect about the line x equals 0. Again, the line x equals 0 is this green line which hasn't moved to x equals 5 or hasn't moved to x equals negative 3. It's the line x equals 0. So if we're flipping horizontally about the line x equals 0, we're flipping about the y-axis, and all of the x values are changing. So this x value is a negative 3, it flips to a positive 3. This x value is a negative 2, it flips to a positive 2. The x value of 0 doesn't get to flip, and the D and the E reflect just the same. And so if we were to connect the A and the B, the A prime and the B prime, the B prime and the C, and all of these as we go, we get sort of a helicopter-like shape, and this is supposed to be a horizontal reflection. Now this is a very simple function. There's no quadratic or radical or rational or linear representation here other than these little breaks and pieces of essentially lines. But this is not a quadratic, and we're just representing this with maybe the name f of x. But again, this is not a quadratic. This is just a random function that I created. So what you might notice is that there were a few points that were not changing. And we saw this definition last year under the name invariant point. Now the word invariant refers to not varying or not changing. So there were a couple points that maybe didn't move. Graph on the left, which point didn't move? You might see that A didn't move. For the graph on the right, C didn't move. So we could say that for the left graph, the point A was invariant. For the graph on the right, we could say that point C was not varying or invariant. So as a bit of a definition, we'll word this similarly as we did last year perhaps, and we'll maybe just call this something in very good language, a very nice language, a point that does not move. And that's simple enough. A point that does not move. And in both of these graphs, the point that was invariant, or the points that were invariant, seem to occur on that green line. So where might invariant points occur for reflections? Maybe we call it that axes of reflection will always be where the invariant point is. So we'll say that invariant points occur on the axes of reflection. And if you prefer to use a different word, you might call it a mirror line, because there is a little bit of a reflection or mirror that happens. So the conversation can be quite quick, but occasionally you'll see questions which refer from one function to create another one. So here's a quick chart which gives us a few x values, and again we don't know what this function looks like except for 4x is the name of the function f, which we should be able to notice there's no radicals or squareds or cubes or division, so this is really a linear function. And so the function f is creating the y value as 4 times the input. So 4 times negative 2 creates a negative 8. We could do this for all the values of function f and say 4 times the input, 4 times the input, 4 times the input, and create some y values on the function f. We could graph this and it would appear linear with a slope of 4. Now we're going to create a new function with the name g of x, and the function g of x is not going to be created from an input necessarily. We're going to create this by a negative y value, specifically from the function f. So we actually look at the function f, which is negative 8, and simply put a negative in front of it, and that gives us our new y value on the function g. So negative of 0, 0. Negative of 12, negative 12. Negative of 20, negative 20. And what we would see is the function g of x looking like a negative of the function 4x. And you should essentially see a vertical flip appear as a negative 4x. That is the function g of x if you wanted its actual equation. So a little bit more conceptually now, what if we were to talk about a generic point a comma b? So we did some actual flipping visually, but what happens if we say there's a reflection about the x-axis? Where is it now? So every point, almost like a mapping notation, is changing to where when we talk about a flip in the x-axis. So it does help to visualize what the effect is. Is it vertical? Is it horizontal? You might even draw an axis and say, there's the x-axis. If I reflect about the x-axis, in the x-axis, on the x-axis, this is referring to a vertical flip. This is affecting the y values. So maybe you say that all the points from AB are now becoming a comma negative b. The y value was affected. For the point a comma b reflecting about the line x equals 0, and visualizing it to ensure we're not doing the wrong reflection, the line x equals 0 is referring to the y-axis. Now this is actually going to appear as a horizontal reflection, which affects only the inputs, the x. So we could say that all the points AB become negative a comma b. And the last question, this one was actually taken from the standards document for 30-1, and it says, when will the graph y equals negative x squared plus 4, when it's reflected in the y-axis, what is the equation of the transformed function? Many people do prefer to visualize this, And if this is reflected in the y-axis, this refers to a horizontal reflection. And it is nice to visualize a flipped function that has been shifted up 4. So this is combining two effects now, which will be a good preview of the next lesson. But flipped parabola and shifted with the vertex up 4. So it would look something like this. Which is the equation that relates to an upside down parabola? Well, not A, not C. That is shifted up 4, not D. It would have to be B. So this is a reflection that has occurred when there has been a transformation or a translation up, as well as a flip. Now, a good side question might be, what would happen if we did a horizontal flip? What would its we'll come back to that last one. If it's reflected in the x-axis, we're talking about basically all the points being the same. So the actual graph did not change. Getting ahead of myself, what if we actually talked about this time a vertical flip? How would the graph change? This one's not quite as simple. If this one were to flip vertically, we notice that maybe the vertex has to flip down here, and then it will be opening up. So some sort of shape like this. So if we were to sketch the new one, maybe it would look something like this. And perhaps we could guess this quite quickly by saying it opens up, and therefore it has to be either A or C. The vertex is down 4, so it would have to be C. So the option would be C if there was a vertical flip. We could even go so far as to say, if this was a vertical flip, we want to say that the new graph, I'll give it a new name, the new graph is created with a vertical flip, a negative of the original graph. So if I were to say, let's put a negative in front of the original graph, what happens to the equation? We end up with a positive x squared subtract a 4. So you can actually create this equation by simply putting a negative on every y value, which is really saying a negative on the function, and create the new function. Regardless, that's a very quick conversation about flips, and we're going to build on that in our next conversation about stretches. So we'll actually look at the next video in 1.2, Part B, stretches.